Hi guys, and welcome to this short video where I will go through the broad topics that are supposed to come in paper 3. Right, so a brief introduction first. So for those of you who don't know, paper 3 had a little change in the structure of the exam in 2021. Right, so the first question, there's still 3 questions, but the first question is an actual lab experiment that you have to do in person and record your results and plot them on a graph, right? So the 4 topics that they give us are graph work basically. Then there's measurement. Then turning forces. And finally transformers. So the first 2 topics are not really that problematic. Graph work simply means that in the first question, you will simply have to fill out a table and plot the points on a graph and be able to find the gradient. Now I already did a video detailing how this is done in my graph work video. I will simply just link it at the bottom in the description and you could watch it there, right? Now measurement is a kind of vague topic, right? There are lots of things that they could ask in measurement. So measurement you could be asked to actually measure stuff using the vernier caliper or the micrometer screw gauge. So there could be pictures of something being measured in the exam and you'll have to record those results or interpret it, and you need to know how to read off the little markings in that equipment, right? So I will link a couple video links on how to read the vernier caliper and the micrometer screw gauge, which are actually very helpful in doing this, right? Now other things in measurement could be the triple beam balance. Alright, the triple beam balance, as well as volume, where you read off the meniscus. Right, and we actually have past paper questions on how to reading of the meniscus and using the triple beam balance and finding density from those, right? So measurement is fine, we could handle measurement. Now, in all the years of paper 3 past papers, there have been no past paper questions on these 2 topics, but we don't need to fear, right? Because if that is so, there's only really one experiment per topic that they could really ask, okay? So for the turning forces, which is essentially moments, right? Moments are turning forces. The experiment is to find the weight of a meter rule. Okay, the weight of a meter rule. And transformers would be, well, we will go into detail about transformers. In order to interpret the experiment, you have to understand a little bit about transformers. So I will also be doing that. But the experiment in transformers will be a theoretical experiment where you have to adjust the coils. Okay, and we'll get into what these things are. Okay, so remember, the change in the structure of the exam is for one of the questions you actually have to do the experiment. Now, I don't believe that they would actually ask you to do the transformers experiment. So the 2 experiments that they could bring are one for the measurement or the turning forces. The other 2 questions will be similar to the past paper questions, where you just have to come up with a lab experiment or draw a graph and interpret some results, okay? All right, so let's get into the measurement part first. So here, Akil was given a large rectangular block of plasticine and he is asked to find the density. So he has a triple beam balance and a meter rule or half meter rule, right? So we know that density, or rho, is equal to the mass per unit volume, which is mass over volume. So therefore, the first thing that he needs to do is to find the volume of the block of plasticine using the meter rule. Right, so he simply needs to measure the length, the breadth, and the height, and find the volume And using the triple beam balance, you can find the mass of the block, and we have to use this formula here to find the density. Okay, so a very simple setup of the experiment here. All right, so there's a graph on the other side of the page. I don't have the graph. That's regular graph work, right? So they said that the graph was plotted, and in the graph you have to simply read off different points on the graph to fill out the table. And it's very simple. One axis would be the mass, one axis would be volume. So you might have mass here and volume, and the graph would be like that. So you just simply reading off the mass, what volume corresponds to that mass, and so you go, and eventually record the table. Right, so in my graph video, you would see how to find the slope or the gradient of the line as well, okay? And these very, very easy marks here for this kind of question. So this is actually fall under a measurement question because they're using the triple beam balance and the ruler to measure, right? So let's take another example now. Here we actually have a triple beam balance, which is this, and we have another way of measuring, which is using the meniscus or the volume of water in the container here, right? So figures 2 and 3 show the mass and volume of a stone being measured, right? So in the first figure we don't have the stone, and then in the second figure we actually have the stone, right? So let's take a look at what is going on here. So this triple beam balance here in this first picture is just measuring the mass of the water on the scale here without the stone, right? So let's see how to read this triple beam balance. It's called triple beam because it actually has 3 different things you need to read from. This is the largest value here, this is the medium, and this is the smallest value, right? So the mass of this water is 100 plus 20 plus, and we have to look carefully here, 2.2468, and this is 2.8. So the total mass is 122.8 grams. Okay, so that is the weight of everything here without the stone. Now we have to measure the weight with the stone. So we could actually take them away and find the mass of the stone, right? So let's try again. So we have 100, then we have 40, and then we have, sorry, no, this is wrong. This is 2.4 actually, my apology. This is 2.4. Right, so we have 0.1, 2, 3, 4, 5, 6. So 0.6. So this is 140.6 grams. So therefore the mass of the stone would be 140.6 minus the 122.4, and you will get 18.2 grams. So as you can see, this is a simple sort of experiment, right? It's simply just adjusting the triple beam balance until it balances, right? So I could actually link another video showing you how to operate a triple beam balance. So this could probably come for the experiment that they actually want you to do. It's a simple one, right? So now we actually have to record the readings. So they want us to also record the readings on the measuring cylinder. So let's take a look at this measuring cylinder here. How do we read what is the volume in this measuring cylinder? We have to look at the bottom of the meniscus. So this curve here is called a meniscus, right? The curve of water. So to read it off, you look at the flat part or the bottom part of the meniscus, which is there. So we could see that this is 50, so 51, 52. So this is 52 centimeters cubed in this one. And let's take a look at the other one. With the stone inside, obviously the stone has volume. So we can measure the new volume. So the new volume will be 60, 61. So I'm getting 61 centimeters cubed. So if I want to find the volume of the stone, all I have to do is take away those numbers. So it will be 61 minus 52, which is 9 centimeters cubed. Right? So you could just fill in those values there. So yes, we use the readings already to calculate the mass and the volume of the stone, right? So this is a very simple question that could also come. Let's take a look at one more measurement question. In this case, we will be measuring time from a stopwatch. We're using a ruler to measure the length of the string. And this is a very simple experiment, again, using the pendulum, right? So they want us to investigate the length of the relationship between L and the period of the pendulum. That is how it swings, right? So they give us this apparatus here. We have the pendulum and the bob here. It's the whole pendulum here. It's attached to the retort stand, so it's there. So the first thing that we need to do is to start oscillating the pendulum, right? And we're using the stopwatch to measure the time it takes for the pendulum to complete 20 oscillations. So what is an oscillation? Well, you could imagine that the pendulum is going to be swinging back and forth like this. So when it goes here and comes back here, that is one oscillation, right? That alone is one oscillation. So to measure 20 oscillations, we count and use the stopwatch, right? And then what we have to do now is to adjust the length of the string afterwards. So you can make it shorter or you can make it longer, right? And to make it shorter, all you have to do is wrap the whole thing along the retort stand. That'll make it shorter, right? You don't actually have to cut the string and tie it back and all kind of thing. You just wrap the whole pendulum along the retort stand and make the string shorter and shorter. And you repeat the experiment and see if it takes longer or shorter to complete the same 20 oscillations, right? What's left for you to do now is to record your findings. So you measure the length of your string. So if it's 0.1 meters to start with, you take the time, right? Then you take the period, and then, well, they have the table recorded for you, right? So this period squared here is the t squared over s squared, okay? Well, sorry, just t squared, my apologies, right? The s is the unit, okay? So as you adjust your length, you keep putting the time, adjust your length, you keep putting and filling out the table, right? And then you could actually plot a graph. They will tell you to plot a graph, and again, graph work is very simple, and you get big marks for plotting graphs in paper 3. Okay, a lot of marks. You don't even have to understand what is even going on, and you could still plot a graph and get full marks, easy marks, right? So make sure and watch that graph work video. Okay, so these kind of experiments are very easy. All right. Okay, so that is basically measurement in a nutshell. Remember, I will link the videos for using the vernier caliper and those things in the description, right? So let's move on to the next topic, which is turning forces, or essentially moments, right? So the moments question will 99% be that you have a meter rule, right? And you want to design an experiment to find the weight of the meter rule using the principle of moments, right? So you have to remember what the principle of moments is, right? The principle of moments, the total clockwise is equal to the total anti-clockwise moments, right? And that's for a body in equilibrium. Okay, so let me show you how to go about doing the experiment, because again, this is a very easy experiment that they could actually ask you to do on the day, right? So your apparatus, what you will need, you need the meter rule, obviously. Right, the other thing you need is a retort stand, just like what we had in the previous experiment with the pendulum. The next thing, you need string, because what you're going to do is you're going to use the string to tie the meter rule on the retort stand. Then you're going to get a set of slotted mass, or slotted weights, right? And each of them could be 100 grams. But you could make it anything, honestly, right? And that should be a day. So your diagram, how are you going to set up this experiment? So you have your box here. Alright, so this is your retort stand on the ground here. Right, so at the end of the retort stand, let's not make that a little too long. Right, so that's your retort stand, and let me use a different color for the meter rule, right? So you are going to attach the meter rule like this, right? So you know the meter rule is 100 cm or 1 meter, right? And in the middle of the meter rule, that is where the center of gravity is. That's where all the mass is acting on, right? So you have to assume that this is the mass m of the or the weight, sorry, because we're doing it force, right? The weight of the meter rule is acting downwards like this. So because I put the meter rule on balance, the meter rule is want to go to tip in this direction, right? Obviously, you could think about that, right? So to balance this, I am going to put the mass now. I'm going to attach some string. So this is attached via a string here, right? This is string. Now I'm going to take some more string and attach one of the weights on this side. So the weight is going to pull down on this side, and it's going to counteract the weight that is going down there, because remember, the principle of moments says that the total anti-clockwise is equal to the total clockwise. So what is the direction of the weight? The weight is going down like this. So that is clockwise. However, the slotted masses that you are putting are going in this direction. So that is going anti-clockwise. Okay, so therefore, whatever moment you get for this distance here and the weight over here, once the ruler is balanced, that will be the weight of the ruler, right? So let's do some experiments and see. So removing this here, oops, sorry. Right. So to find the moment for the weight, we take the W, which we don't know, and we multiply it by the distance from the 50 cm mark. So remember, the center of the ruler will be the 50 cm mark in a meter rule. And we measure the distance from the string to the 50 cm mark. So let's pretend this was like 10 or something, right? That's 10 cm there. And now we need to take the moment about the weight. Now we know the weight because we said it's 100 grams, right? But what slotted weight mean is that you have like a bar here, and you could put more, and you could put a next weight if you need to, right? That's what it means. They could go on top of each other, like how weights is in a gym, right? So let's just pretend we have the 100 grams here. We could just put it in kg, so 0.1 kg. But remember, moments is in force, right? So we need to actually multiply it by 10 to get the force or the weight of those weights, right? So it could be 1 Newton, right? Because 0.1 by 10 is 1. And then you measure the distance from wherever you attach this to the pivot, right? So let's just pretend this is probably like 30 cm. So you use your moments formula. So the total anti-clockwise moment would be 1 Newton multiplied by the 0.3 meters. That should be equal to the weight multiplied by 0.1 meters. Right, so this will be how you find the weight. So let's just pretend. So we have 0.3 over 0.1, and the weight of the ruler in this case would be 3 newtons. Okay, this is just an example. You don't actually have to calculate anything in these kind of experiments unless you actually have to do it, right? So in some instances, they might ask you to plan and design a lab, right? Which means that you're telling them what apparatus you're going to use, you draw the diagram to show how you're going to use it, but you don't actually do it, right? But in the event that they do ask you to do the experiment, now you know what to do, right? So that's how you could find the weight of the ruler. Now, you can't just do the experiment one time. You need to do the experiment at least maybe 3 or 4 times to find the average weight, because you know there are errors that could crop up in an experiment such like this, right? So what you could do in the next scenario is you could either shift this weight more to the string, right? So reduce the distance, and that shouldn't cause any problems. You could increase the weight of the slotted weights and shift it a little closer to the string, so you get some different values, but it would always work out to be the same weight once you are correct, right? So you repeat the experiment a couple times. So let's just pretend now that we put 2 newtons of weight now in the slotted weight, and we shift it I don't know, 20 cm. Obviously I'm just going by guess here, right? This is probably not going to work. Maybe okay, we increase the weight by 1.5, right? And then we have the weight, and we always keep that at the same distance, right? 0.1. So let's find the weight now. So it's 1.5 by 0.2 over 0.1 will give us our weight. So let me just put this in the calculator to see if by chance we get the same thing. Give me a second. Alright, so 1.5 by 0.2, and then divide that by 0.1. Yep, so we get 3 newtons is the weight. So you see how we adjusted the values here, right? By simply putting in some more weights or adjusting the distance between the weight and the string or the pivot, right? And we get back the same weight. So this is how you repeat the experiment a couple times to get different values. So if you get different values for weights like 3.1 or 3.2, that's fine, you're still correct. You just at the end now you need to find the average weight. So if you repeat the experiment a couple times and you get 3, you get maybe 3.1, and you get 2.9, you divide that by 4. That's how many times you did the experiment, and your average might be 3 newtons, right? So your average weight of the ruler, 3 newtons. In an experiment like this, just remember that the weight is in newtons, right? That's the SI unit for the weight. And there you go. That should be your turning forces or moments in a nutshell there, right? The next part now finally are transformers. So there's only again one experiment that you would not, I highly doubt that they would ask you to do the experiment. So this might be just a plan and design, or they might give you the experiment and ask you to fill out a table and draw a graph or something, right? But before we get to that, let's just talk about transformers very quickly. So in a transformer, this is basically a charging brick, right? So you know about transformers. Transformers could be on your light poles, and it could also be like to charge your phone. That charging brick is a transformer, right? So what transformers do, they take alternating current through one side. So this side here, we call it VP, right? And then it changes it. It either increases the voltage or decreases the voltage through the other side. We call it VS. So how it works is that there's a iron core, right? So there's a piece of iron. This is the piece of iron here, and wire is wrapped around the iron, right? So a lot of coils are wrapped here in the primary section. We call it VP, so primary coil. And then another number of coils, so some different number of coils are wrapped in the secondary section. We call it VS, as the secondary voltage, right? So for example, 120 volts might be coming through there, through a power outlet, and then giving this to your phone, it converts it to 5 volts. So that's how transformers work, right? They simply adjust the voltage, right? No big deal there. So it works with alternating current, not direct current, but these things are probably not important for your paper 3, right? What is important here is that they are step-up transformers. Step-up transformers means that they increase the voltage on the output, right? So if, for example, 120 volts might become 240 an output. But the most popular ones are step-down transformers. So step-down transformers are like your phone chargers. right? They take 120 and convert it to 5. Okay, so let's take a look at some of the uses of transformers. So when your local electricity company is sending electricity, some of the power is lost as heat, right? So in order to prevent large amounts of energy being wasted as the heat, um, the resistance of the cables should be kept as a minimum, right? And when resistance is at a minimum, voltage is at a maximum, right? So a step-up transformer is used to increase the voltage as high as possible only when transporting it to your home, right? Through the wires on the light poles, right? Now, when the electricity is ready to reach your home and be consumed by you, right outside your house, there's a step-down transformer on the light pole outside your house, right? And that actually decreases the voltage so that most of your appliances could run, okay? So that's one use there. Now let's take a look at the calculations. There's only one formula you need to learn in transformers, which is this one here. Okay, so this states that the primary voltage over the secondary voltage is equal to the primary number of coils. So you could actually count the coils, right? Over the secondary number of coils, and that is equal IS over IP. So I is current, right? So the secondary current over the primary current. Now notice something here. They went from VP being equal to NP, but NP equal to IS. Okay, so you have to look out for that, right? The I is flipped, the current is flipped on the end there, right? So VS, NS, IP. So keep that in mind, right? So that is the formula, and we will look at an example on how to use this formula, right? So let's take a look at it. So here we have a transformer. So the primary coil of an ideal transformer is connected to a 120 volt main supply. So this is the VP, right? That's the primary coil, and is used to operate a 60 watt 12 volt device, right? So we want 12 volts. This is our secondary voltage. The primary coil is wound with 4,000 turns of wire. So this is NP. So what they want us to note now, they want us to find the number of turns on the secondary coil, NS. So we have VP, we have VS, we have NP, so it's very easy to find NS. So VP over VS is equal to NP, sorry, my apologies. NS over NP is equal to VS over VP, right? So NS is the thing we're trying to find. We have NP, which is 4,000, VS is 12, and VP is 120. So all that's left to do to find NS, we take the 12 over 120 and we multiply it by 4,000. So we bring this 4,000 on that side, right? And you will get 400 coils or turns of wire, right? Okay, the next step now is they want to find the current in the secondary coil. So this is very simple. There's from the electricity formula, we have P is equal to IV, right? So we know the power. This the device is 60 watts, right? So 60 will be equal to I, and we know the voltage of the equipment, which is 12. So to find I, we just take the 60 and divide it by 12. So I, which is current, is 5 amps. Alright, very simple. The next step now, they want to know the current in the primary coil. Now, they didn't give us any information for P for the primary coil. They just told us that the device for the secondary coil was 60 watts. So how are we going to find the current in the primary coil? Well, this is where the next part of the transformer equation comes in. Remember, we have the IP over IS in the end, right? So we could use IP over IS is equal to VS over VP. Right, so let's see. So IP is the thing we are trying to find, right? Because you know we already find the current for the IS, which was the device. So that's over 5, and this is equal to VS, which is 12 over 120. So again, to find IP, we just take the 12 over 120, we multiply it by 5, and you get 0.5 amps. So yes, they could ask you to use your transformer equation as a, like a 5-mark extra in that part of the question. So this is just transformers and calculations in a nutshell, but let's get to the bulk of what the question could be. Right, so this here is the experiment that would come, right? Almost guaranteed to come. So the experiment is to investigate the effect of the ratio of coils between the primary and secondary coils. So remember, there's a difference in the number of coils in the primary and the secondary, right? And that would control how much the voltage either decreases or increases. Okay, so the hypothesis here, if they ask you to plan and design an experiment, would be that the output voltage or the secondary voltage is dependent or directly proportional to the ratio of the coils between the secondary and the primary coils. Okay, so let's see how we could do this. So you set up the circuit, right? And you have a set voltage in the primary section, right? So in this case, we set the voltage to 24 volts. And we keep the number of coils in the primary coil at 1000. So we wrap the wire 1,000 times in the transformer. This is why you will not actually have to do this experiment. It will take hours, right? So this is a theoretical experiment, right? So what we are changing is the number of coils in the secondary part of the transformer. Okay, so now we have a table here. They will give you a table, and they will give you the number of coils on the secondary coil. So if we start, remember 1,000 is always on the primary coil, right? So if we start with 100 coils in the secondary coil, the ratio of the primary coil to the secondary coil, the secondary coil to the primary coil, so NS over NP will be 100 over 1,000, which is 0.1. As you move up, you reach 200, well, it's 200 over 1,000, and that is 0.2. And so you go, right? So you reach 300 over 1,000, 400 over 1,000. That's the ratio, right? The only thing it's changing is the number of turns in the secondary coil. The primary coil is staying the same at 1,000. Okay, so you would get those values now for your ratio, right? And then you would be able to measure the voltage, right? But you can measure the voltage on your voltmeter, your theoretical voltmeter, right? And you will get different values. So what you notice here, the voltage is increasing, right? Look, it's going from 2.4 to 4.8, and it keeps increasing as the ratio keeps increasing, right? So it's going from 0.1 to 2 to 3 to 4. So as the ratio of the number of turns in the secondary coil to the primary coil increases, the output voltage will increase as well. So this basically means the more turns you have in your secondary coil compared to your primary coil, the higher the voltage is going to be as our output. Okay, so they could ask you to draw a graph of the table showing the output voltage. That's what you have here, right? Versus your ratio. So this is the ratio over here, right? So the ratio, forget this N1 and N2 thing that they have here, right? What we're using is NS to NP, right? Your secondary turns to your primary turns, right? So to remember to plot your graph, you just look at the 0.1 and you line it up with your 2.4, right? You could again go back to the graph video and you will learn how to do that, right? And so you go and you construct your best fit line. Very simple, right? So you could see from the graph, because it's a straight line, it is directly proportional, right? So the output voltage is directly proportional to the ratio of the number of turns of the secondary coil to the primary coil. Okay, so I hope you guys learned something from this video. This is actually what is going to come for your exam, right? There's no other experiment that transformers could bring. There's really no other experiment that moments could bring. The only thing is measurements, as I said, has a couple different things that it could bring, and I'm going to link the video down in the description so you can actually view those videos. Okay, so thanks for watching, everybody.